Okay, so I think the characteristics of geothermal energy developments in the Netherlands, probably a lot of you know what is going on. I mean, there are several projects of deep geothermal. I need to maybe emphasize that we are talking about deep geothermal developments here. I'm not talking about shallow heat pumps, etc. So the focus is on deep wells, and so it's primarily associated with greenhouse operations at the moment. That's why I chose this background picture here, where you see a drill rig plus the greenhouses. And there are many challenges associated with the development of geothermal energy. But I focus on the geological, technical, and scientific challenges because all the other things that are involved with, let's say, legal issues or economics, etc., they're also interesting, but nothing that I want to talk about here at the DeepNL meeting, and that's also nothing I know a lot about myself. So maybe I decided to start with this slide. It's a slide that I almost show in every intro lecture of geothermal energy when I teach, when I explain what deep geothermal energy is. So we say, okay, the provision of heat and or electricity through direct use of geothermal resources. For what do we need for that? We basically need a thermal water loop where we have a production well, where hot water is pumped to the surface, where it's used in a heat exchanger to transfer the heat to a working fluid that goes into a heating system or a power plant or whatever. And then that way it's cooled down, and when it's cooled down, it's re-injected. And that way we have a closed loop. The temperatures we are looking at are something like, I wrote 100 here, but that's for electricity. We could go down to 60 to maybe 200 degrees, depth of 2 to 5 kilometers. In the Netherlands, we talk about less than 200 degrees, of course. So that can be used for power plants or district heating systems, where you then have a working fluid cycle that goes either into a turbine, which is for a power plant, or it goes directly into the heating network. So what are the challenges that are associated with developing such a system? So first of all, as many people forget, that the primary challenge is to find the reservoir. Okay, in the Netherlands, we have developed, or in many places in the world, we actually developed geothermal resources where we knew that the reservoir was there for various reasons. But if we don't know that, then the primary challenge is to find it first. Then if we have it, we need to develop it, sometimes stimulate it, because if it's not productive enough. And of course, at the end, we need to produce and convert heat efficiently. For that, we need a good understanding of the connection between what we have in the subsurface and what we are doing at the surface. So surface technologies with geosciences need to be combined. So we'll start with the first challenge, finding the reservoir. So I really like this paper that Harmen Meinlief published earlier this year about the geothermal plays in the Netherlands, where he explained, where you can actually find geothermal reservoirs in the Netherlands. And the kind of primary ones that we are exploiting these days is the porous reservoir. It's very much associated to gas reservoirs or let's say hydrocarbon in general, where we knew that there was hot water as well. So that is exploited. So there are hot sedimentary aquifers with high porosity. Usually the heat comes from below by conduction. Sometimes you have also convection in your reservoir, or actually even below the reservoir, which means that you can have temperature anomalies. If you look at this temperature depth curve here, you can see that, if you have convection, you can actually have higher temperatures than you would have in a normal conductive thermal gradient. So you would deviate from the average of 31 degrees per kilometer of temperature increase with depth. And of course, then you can also have a decrease. You can also have a negative effect if you're in the downwelling part of the convection cell, and then it's actually colder than you would expect. Okay, but you can, if we don't find a porous reservoir, sometimes we like to go close to fracture or fault zones, because then if the reservoir itself or if the rock that we are targeting is not that permeable, actually the fracture zone may cause, the fault zone and may actually cause for extended fracture zones that provide enough permeability, even if the rock matrix itself is not very permeable. So that's a kind of other type of play that we are looking at. And of course, something that we are not doing in the Netherlands yet is EGS, but that is, if you have tight reservoirs, you try and stimulate them, you enhance productivity. That's why they're called enhanced geothermal systems. This is what we are probably expecting to do if we go for ultra deep geothermal, or at least what we should reasonably expect that we will have to do that. So when you go for ultra deep geothermal, which is one of the plans in the Netherlands, that we at some stage go for the ultra deep. So from that paper that Harman published, he actually listed all the different play types or potential play types. And I just looked at the one that is one of the two most, let's say, productive ones is actually this Upper Jurassic or Lower Cretaceous Delft sandstone, and what is above and below, which can be primarily found in the southwest of the country. So that's why it's called the Delft sandstone, because that's where we find it. If we look at it, it's really, if you compare the this Upper Jurassic with transmissivity, the transmissivity of the reservoirs plus the temperature, you can see that this is a good fit. So both it's productive enough and warm enough to have deep geothermal operations. And that's why we have a lot of geothermal projects actually developing in the Westland area and Rotterdam and etc. Also our deep geothermal well on campus of TU Delft, which is actually an EPOS-NL infrastructure, is part of this. Also in the same region, we can go for the Triassic, or at least it has been proposed that the Triassic, mainly the Buntsandstein group, would provide, let's say, suitable properties for exploitation. So it would be permeable enough, and because it's relatively deep, it would be also very hard. So far, we only have one operative project, the Vierpolders project, that produces from the Buntsandstein. And one unsuccessful project was the Trias Westland project. They're now successfully producing from the Delft sandstone, I have to say. But when they tried to go to almost 4 kilometers depth into the Trias, the rock was really very dense. So that's really a challenge. Another one we find in that region, it could be the limestones from the Zeeland Formation on the Carboniferous, which could be the target for ultra deep geothermal. It's not been drilled into yet, so we don't know. It has actually been developed further east in the Ruhr Valley Graben, or in Limburg, where we have this play with the fault zones, where actually the permeability is relatively good because of the fracture zones close to the faults. Those were two geothermal doublets that were developed there and operated until recently. And I'll talk about those a little later. So if we look at the Rotliegend, which is another major target, that's actually more developed in the northwest of the Netherlands and in Groningen. In Groningen, it's probably not so clever to exploit it for geothermal at the moment, because this is all, let's say, where you have extensive gas developments. Geothermal is probably not so clever to do. So we look primarily at the northwest region, like here, where you see on the left where the transmissivity is positive here. So we have 6 deep geothermal wells, like in Middenmeer, in Andijk, in Littelgeest, and in Kuckuckspolder. They're all around here. Well, this part here we leave untouched for the time being. So if we look at what we have so far, so 12 of the successfully developed projects are in the Jurassic or Lower Cretaceous in the southwest. 8 projects are in the Rotliegend. Then 2 are in the Lower Carboniferous. So that is in the California projects, like in Limburg. And then we have 1 in the Triassic and 1 in the Cenozoic that I didn't really mention yet. The Cenozoic is relatively shallow, relatively low temperatures that I'm not considering here. Most projects actually were developed for heating greenhouses, as you can see down here. 1 for district heating and 1 for a combination of district heating and greenhouses. So this is what we know so far, and that is basically, if I may say so, the low-hanging fruit that we have developed, even though it was challenging enough, because those were the reservoirs that we knew. We knew they were there. We knew they could be exploited. Some of them were a little more challenging than others. So when I say we knew that it was there, it's, you know, the Trias Westland, we was not successful because it was an adventure. We said, okay, the operators were adventurous enough to say, let's try. You know, there is no well nearby that has shown that the Trias is good. In other places, it was good enough. But actually in the location in the Westland where they didn't drill, it was really tight. And so no developments in the Trias. But other than that, usually the reservoirs were fairly well known. But if we go to other places in the country where we don't know the reservoirs yet, so what do we do? Actually, this has been recognized. That's why, you know, there is this SCAN project, which is led by EBN, to develop more, you know, or to reduce the number of white spots on the Dutch subsurface map. And that is also to help geothermal developments in other places than the ones that the hotspots that I have just pointed out, and that we are going to look at later today as well. So this is a seismic campaign for the geothermal developments in the Netherlands. The question is, you know, it's very difficult even from seismic to define where your geothermal reservoir is. So will the seismic data be sufficient? That is the question I pose here. The challenge is to really still, you know, even with these additional seismic data, to define hot sedimentary aquifers, because they're not defined by typical structures that we have for oil and gas. Like for a trap like here, you know, we don't necessarily have that for aquifers. Sometimes we do, but we don't need them. Let's put it like this. So that you cannot identify permeable zones from seismic alone. Maybe you can define fracture zones, but like the permeable zones are very difficult to see. So you see structures, but you see no fluids. So you don't know if the structures you see will actually have fluids in them. So there is, of course, electromagnetic data would show fluids. They're most, no, shouldn't say they show fluids, but they are more sensitive, let's say, to fluids. So they could show the presence of fluids, but of course the resolution of electromagnetic data is much less than for seismic, and also especially with depth. So one thing that we really have to also understand when we look at these data is, do we have faults? Those we will hopefully see in the seismic, but what we don't see is if they're sealing or if they're transmissive. So what is their potential role in a reservoir? And of course, what we also don't see on what we need to know is, can these faults be reactivated? What is the, you know, what's the risk of induced seismicity if we have operations near such a fault? These are things that need to be addressed, of course, when we want to develop an area with a fault. So looking at the design of a geothermal reservoir. So what are we interested in actually? It's primarily, we want to have good lifetime. So we want to make sure that the geothermal reservoir is not exploited too quickly. We want to get the maximum amount of energy out of it. And of course, we want to do that at the minimum of cost. So reduce costs, but maximize energy output. So what we need to look at, of course, is the permeability of our reservoir rock. We need to know what the saturation is, so how much fluid do we actually have down there. And of course, the depth and temperature are also relatively important. Now, the trick is, of course, finding the right combination of heat, water, and permeability at reasonable depth. So why is all this so important? I mean, one thing that is really critical in a project is of course, in a geothermal project, not only geothermal, but in this particular case, we're looking at geothermal, is where you place your wells now, right? So your production and injection well, if they're too close together, what can happen is, of course, that you have a cold water breakthrough too early before you actually have recovered all the energy that you would like to. So what happens is, of course, because in your reservoir, the cold fluid flows towards the production well, eventually you will have a cold water breakthrough, and then the project has to stop if you have like a drop of more than, I don't know, 10%. It's something you need to define beforehand, of course, you know, what is acceptable, 5 degrees or 7 degrees or whatever temperature drop before you actually stop operations. So you don't want that to happen too early. That's why, of course, you like a wide well spacing. The risk is, of course, when you have a relatively wide well spacing, is that you need a lot more pumping energy to circulate your fluids, but also the heterogeneity of your reservoir is something that is very difficult to control, you know, or impossible to control, and but very difficult to also factor into your calculations, because if you don't really know your reservoir, then you know it's very difficult to plan. But the larger your well spacing is, the higher the risk that the heterogeneity actually works against you, so that you will lose hydraulic connection or something like that between your wells, or that you have a fault between your production and injection wells. Now, just to give you an impression, that's from a simulation we did, you know, to calculate breakthrough times based on well spacing, so the distance between production and injection wells. So we start at an, you know, temperature of 100 degrees, and we, you know, if our well spacing is only 250 meters at the fixed flow rate, you know, the breakthrough time, so when we lose 10 degrees already after less than 20 years, that's clearly not very attractive. And the larger our well spacing is, the longer the breakthrough time is. Actually, these are arbitrary numbers right now. In real operative projects, we have neither 100 degrees so far, or very rarely, and nor do we actually have these very narrow well spacings. Usually we have something above 1,000 meters or 900 to 1,500 meters or something like that in well spacing in the Netherlands. So now the next challenge on this slide, on my intro slide here, was the development and the stimulation. So how do we do that best? Now we have decided to drill, to establish our wells, and now we want to develop them. Now, one thing that we have to be aware of is, of course, that, you know, the deeper we go, the higher the temperature is, but also our permeability decreases and the porosity. That is a well-known thing. Also, from, you know, you can look at this data set from the Rode-Ligand. The deeper we go, the lower our porosity is, and porosity and permeability usually scales with porosity logarithmically here along this relationship. So that means if we go for higher temperatures, we usually go for denser rocks, and that means that we actually need to stimulate. Sometimes, you know, I actually got this slide from Anne Plaumakers. When I told her that I have to give this lecture, she said, "Oh, I have a good slide for you if you want to use that." So I decided I have to use this slide. So with increasing depth, we have increasing temperature, but we have decreasing permeability. So if we go deeper, we may want to use fractured reservoirs because the porosity actually goes down. Then the fractures supply the permeability. But of course, these fractures may not be conductive. So, you know, we need to maybe stimulate them, but if we want to minimize the risk of induced seismicity during stimulation, we should know how do our operations affect size and location of stress changes in the fault systems, and how do operations change the mechanical and chemical equilibrium in our fault systems. So we have a choice, if we want to, if we have our dense reservoir and we want to enhance it, there are several enhancement techniques, like we have chemical methods. They're usually used to remove formation damage, which means that's usually something that is very close to the well that results from drilling. And formation damage is that the drilling might actually go into the open fracture zones and clog them, and that can be solved with acidization usually. Similar thermal methods, if our near wellbore area is actually not very permeable, then thermal methods can help to overcome this. You basically throw down very cold fluid, and so the thermal shock will lead to fracturing, actually shrinking of your rock, and that opens additional fractures. This is actually particularly successful if you have very hot wells. And of course, then mechanical methods or hydraulic methods include, you increase your inflow area also way into the reservoir by hydraulic fracturing or shear fracturing. And of course, all these methods can be combined. You can have combined mechanical chemical. That means that you actually, when you do hydraulic fracturing with high pressure fluids, that you actually have a, let's say, chemically altered water down there. So the chemistry will also help. Actually, this method helps to also dissolve material further away from your well if you want to stimulate also right into your reservoir. Of course, everyone, when we talk about hydraulic fracturing, the immediate reaction these days is, what about induced seismicity? And this is a picture of the Bruhn earthquake in Korea, which was a few years ago, and that made it into science and into major headlines. So this is, of course, something we want to avoid. And the first thing to avoid this is, of course, as it relates to challenge number one, finding our reservoir, is to know that there is a fault. That was the main problem in Bruhn, wasn't that they were careless or anything. It's just they didn't even know there was a pre-stressed fault. So they only discovered it after they triggered it. And that is something we want to avoid. So these are basically, there's a other famous science publication here. What are the two major mechanisms that we look at? And this, of course, touches a lot of what you're doing in DeepNL. Is either we have a volume and mass change by massive extraction of something like what was done in Groningen over the decades, and then that can reactivate faults in the subsurface. What is actually more interesting for geothermal, because we actually don't change the volume in the subsurface so much because we re-inject, but we can increase pore pressure along a fault. And this can also trigger, of course, seismicity. And this is what happened in the California wells in Limburg. So there was seismicity in Venlo, which was associated with operations in the geothermal wells. It was not very strong, we have to say. I think the initial quake was magnitude 0 or something, but operations were halted. And then there were several aftershocks. One was even 1.7, which is not that big, but of course people are worried that it could be bigger. So I think for the time being, there will be no operations near those faults anymore. So generally, induced seismicity in deep geothermal energy can be related to fluid injection, which then depends, of course, on injected volume, but also in injection pressure. Those are things to control. But it also varies significantly in tectonic setting, of course. It's more likely to happen in seismically active regions. But it's dependent then on the orientation of fractures and faults, the stress state, and the orientation of the stress field, which is also not necessarily static, because the orientation of the stress field, at least in years, can change with seismicity and with operations. So these are things we need to keep in mind. But if we want to mitigate effects, then we have to have, of course, controlled injection. We need to control pressure and volume. We need to monitor everything in the subsurface. We need to be very clear about the local stress field. And we have to know where our faults are. I just mentioned that. What is actually also needed to, and that is actually the non-technical challenge, but something I would like to mention is what we need is also regulatory guidelines for what is actually the maximum acceptable ground shaking. You know, how much do we actually accept? So the magnitude is not a right, let's say, unit to go by, the right parameter to judge whether or not something is acceptable or not. It should be the ground shaking, how much ground shaking is acceptable, and how much is, when is what is the limit that we cannot exceed. And that needs to be also the basis for construction standards for buildings. So buildings have to be able to withstand certain ground shaking in seismically active regions. That means if we don't have that amount of shaking and you still have like a crack in your house, then it's you cannot blame the earthquake for it. You should really blame your constructor for it. That's the quintessence of this, the essence of this, the need of these guidelines. Let's put it like this. Now, another challenge that's really important for completion and operations is the geothermal fluid itself, because it's a multi-phase substance, so it contains gases a lot. So you have two-phase flow sometimes. It's high temperature, so usually it's quite reactive. And it's transported in the pores and fractures of a geological formation, so in the reservoir, where it interacts with the rock. And so it's usually not a beautiful, clean water. It's actually a brine that, and it's the brine properties influence permeability. So it's a very saline fluid. It is usually denser than pure water. It has a viscosity is affected by the chemistry and of course the pH. And all these factors affect your operations. And your fluids, of course, then also interact with your installations, not only with the rock. So, and just to give you an impression, the salinity of geothermal fluids usually increases with depth. But so most fluids are brines, so they have a high salt content, and that means they're very corrosive. The highest known salt content of a geothermal fluid was in the Salina Formation in the Michigan Basin in the US, with a total dissolved solids of 643 grams per liter. Okay, so that is really a lot. The salinity of seawater is more like in that range, 10 grams per liter, something like that. And you can see here on this is actually data from Germany. I have to apologize, I didn't have a similar data set for the Netherlands. But what you can see here with crystalline rocks and sedimentary rocks, salinity increases with depth, but you can have also exceptions where you have low salinity or even at greater depth. And I'll show this here. If you go here, for example, in the Upper Rhine Valley, is independent of, usually most let's say, operations go into the basement rocks. So you have a combination of fluid sea, crystalline and sediments alike. In the Upper Jurassic limestones in Bavaria, you know, south of Munich here, Unterhaching, actually salinity is extremely low. It's one of the reasons why this is such a popular area for geothermal developments right now. They don't have a lot of issues with their water. And of course, in the Rotliegend, which is very similar to the Rotliegend we have also in the Netherlands, the clastic and volcanic rocks in Großschönebeck, we had also more than 250 grams per liter dissolved solids. So another issue that is important to differentiate or to know is, do we have a carbonate environment or do we have more sulfates? Sulfates here, especially barite, require very high temperatures and a reductive environment to become soluble. So it's very hard to remove once you have that. While calcium carbonate is a bit easier to deal with. It's still unpleasant to have. It still reduces your well diameters, and so potentially the injectivity of your and productivity of your system. Now, all this also has an effect on the production and operations. So the challenges of operations are also very much linked to what I just said, to the challenges of the development. So, you need to design your technical components and layouts, which is like the downhole pumps, the heat exchanger, the cooling system, but also the heat distribution system, to be as efficient and safe as possible in your operations, but also to account for what you find in subsurface. So especially the fluid chemistry, but also, of course, permeability in the subsurface, also the risk of induced seismicity. This all affects your layout and your operations. And specific technical risks you have is, of course, the lifetime of a downhole pump, which also suffers from the fluid chemistry and from the high pump rates. So I've seen most economic models of geothermal developments in the Netherlands. They think that the downhole pump needs to be replaced every 5 years. So that's factored into calculations. If you talk to Baker Hughes, a company that supplies the majority of all downhole pumps for geothermal operations, I think there is only one in the Netherlands that has actually lasted longer than 5 years. And most other pumps don't even live 5 years. So that is something that needs to be kept in mind. And maybe there will be some clever engineers who accept this challenge to develop better pumps. The fluid chemistry, corrosion and scaling is a real problem. It affects installations and the injectivity and productivity of wells. That means that we can also, I shouldn't say reservoir pressure, it actually affects injection pressure. If injectivity is poor, we need to increase injection pressure, which then can also have other risks that we may not want. Now, an example of something that was really spectacular actually was the lead scaling from the Rotliegend in Kuckuckspolder. Kuckuckspolder is a real success story because it's hot, very high flow rates. It's a superb reservoir, fantastic project. But after 1 year, all of a sudden, injectivity went down to almost 0. And when they actually looked at the deposits, they found this here. This is under the electron microscope here, and analyzed it in EDX. And they found this peak here, which is clearly showed that it's lead. It's pure lead. So they had precipitation of pure lead from thermal water. And why is this? And that is because they had an exchanged reaction of the fluid with the casing material. So that's why I'm saying, it's important to know your fluid chemistry before you actually choose your casing. So they had to solve this chemically. So basically what happens is really you have a redox reaction between the steel parts and the geothermal insulation and the thermal water. But in the Rotliegend, it's well known that we have metal deposits. Actually, some of the major copper deposits in Eastern Europe are actually in the Rotliegend. So you find lead and copper precipitates also from many brines in the southern Permian Basin. Now, there was another problem associated with the lead precipitation in Kuckuckspolder because it was the lead 210 isotope, which is a norm, so a naturally occurring radioactive material. So even though concentrations are very low, so there isn't really a major health risk or anything, it's something that needs to be taken care of. So you need to take that into account in your operations. So how can we prevent scaling? Oops. How can we prevent scaling? One thing is pressure maintenance in a closed system, right? Which means we keep the system under pressure all the time so that we have no precipitation from the brine. That can be done if there is no reaction with, no electrochemical reaction, of course. Inhibitor, that is what they are now doing in Kuckuckspolder. You have a chemical inhibitor that stops the reaction, prevents a reaction of the fluid with the the casing or with any kind of metal parts, it's a relatively expensive thing, and it has to be done continuously. So that is doesn't make it really very cheap solution, but it works. There's a very new method, or something that has been discussed very recently. It's electromagnetic water treatment. It is something that has been shown to work in some places, depending on the frequency of the treatment, or on the electromagnetic frequency, I have to say. And it's not really understood why it works, but in some cases it has shown to work. So it has reduced scaling if the water was treated before. But of course, a really important thing is if you have the option to do that, so if you know your fluid chemistry before, you use alternative materials for well completion and for your installations. And that way you can avoid the reaction and you don't need to treat it like with inhibitor. That may be more expensive at the beginning, but probably in the long run, it saves you a lot of money and trouble. So other challenges I haven't really talked about is the project economics, because that depends on a lot on subsurface properties, on the layout and the design, and on non-technical aspects, like for example, subsidies. But also the legal framework is very important, because if an investor needs to know that his investment is safe, so that it needs to provide security for the developments. Things like CO2 pricing will play a role. If CO2 has a price, things like geothermal energy become a lot more attractive. The mining law needs to be reliable, needs to enable, let's say, enable us to do geothermal, to drill, to produce the hot water, etc. We need to take into account environmental aspects, of course, and then the public acceptance is a major issue. So as long as nothing goes wrong, communities are usually fine. But of course, in areas where you have natural seismicity, or in places where you have had an induced earthquake, it's very difficult to say, okay, let's do another one. So communication is really, really important, that the population knows what you're doing and that they are supportive. Otherwise, this could be a killer of any project. So, and with that, I would like to finish and thank you for your attention and look forward to your assignments now in geothermal.